Okay, let's get started, please. So remember what we were up to. We were talking about the gamma function, right? We defined the gamma function initially on the right half plane, and then we basically extended the gamma function like step by step until we got a. So it was, remember that it was. It was holomorphic on the right half plane, and then we extended to a meromorphic function on the whole plane that has simple poles at the non-positive integers, right? The way we did that was by showing that we could get the way we got that it was we showed that it was analytic on the right half plane by our usual trick of showing that it's the that we can find holomorphic functions that uniformly converge to it, right? So that's with that we'll and then we extended it. We showed that it's satisfied. Then we showed that it satisfied this equation, right? That it satisfied this sort of relation, right? Actually, we did that. I think we did that before we did that before we extended, right? So this was done. We got this equation first, and then we showed that we could get the extension, right, to the whole plane. So, right. So one, we defined gamma on the right half plane. We got this functional equation. We extended gamma to the entire plane, and it has poles at 0, -1, -2, etc. Right? Okay. So at this point, we make kind of a funny observation. So observe. If we think about, if we look at this statement, okay, each of these things makes sense on the whole. Now these things make sense on the whole plane, excluding these points, right? So, right. So this makes sense. Now makes sense, right? This is actually now a holomorphic function on the whole plane, modulo -1, -2, etc. Right? And this thing is also a holomorphic function on the whole plane, excluding 0, -1, -2, blah, blah, blah. Right. Right. And in fact, at 0, this thing has a simple pole, right? Gamma has a simple pole there. Multiplying by s makes it a removable singularity. Okay, so it actually you can extend it to a holomorphic function on the same region, right? On the same region. So right. So both the left-hand side and the right-hand side define holomorphic functions on the same set. Further, we know that. So just considering them independently. So if we think about this is a holomorphic function on this set. If we think about this, it's also a holomorphic function on the same domain, right? And further, we know that these holomorphic functions equal each other on the whole right half plane, right? So what does that tell you? That tells you that, in fact, they must be equal on the entire plane, right? For all S, right? In excluding excluding those guys, right? So the functional equation actually holds true on the entire, wherever these functions are defined. Yeah.
Is this by like analytic continuation?
Exactly. Yeah.
Okay.
By analytic continuation, right? Because you see that if you could say if you want to subtract one side from the other, right? It has zeros on the entire right half plane, so it must be zero everywhere. So they're equal everywhere. Right, so that's kind of a funny way to extend the functional equation to the entire plane. Okay. Okay. So yeah. So at this point, we're going to show that we can extend gamma to the plane in a somewhat different way that will be useful in what follows. Okay, so I'm gonna erase this. Okay, so this is a alternate way of extending gamma to C, excluding these guys. Okay, so again, we'll start off from the right half plane. So on the right half plane, we have that we have our original definition. This is the integral from 0 to infinity, e to the negative t, t to the negative, t to the s minus 1 dt. And then we split it up into two parts. Okay, the integral from 0 to 1, and the integral from 1 to infinity. Okay. You can do exactly the same kind of argument that we had before to show that that this actually defines an entire function. Okay, so this we're going to break it into two parts. This defines an entire function, and what we're going to do is we're going to find an alternate expression for this left-hand side that will extend that we can extend to the entire plane in a more meromorphic manner. So we're going to show that this thing can be expressed as a meromorphic function, and that will give us a way of again, it will give us a way of expressing gamma as a meromorphic function with poles in the right places. Okay, so that's the trick. It's instead of doing the sort of bootstrapping thing, we're gonna break this up into two parts where we've got one meromorphic function and one entire function. Okay, so and the way we get that meromorphic function is pretty straightforward. So if we considering this thing on the left, we're just going to take the power series expansion of e to the minus t. Right, so you get negative t to the n over n factorial, and from 0 to infinity, and t to the s minus 1 dt. So you just use the power series expansion. The good thing is that this power series expansion converges uniformly everywhere, and so we can pull the sum out. Okay, so we pull the sum out. So since we have uniform convergence, we can pull the sum out. we get negative t to the n over n factorial, t to the s minus 1 dt. N goes from 0 to infinity. Okay. A little bit of calculus gets you to negative 1 to the n over n factorial n plus s as n goes from 0 to infinity. So this is the thing that this is the expression we're gonna use, right? So you see that it has, right, it has poles in the right places, right? Like it has poles at 0, when s is 0, -1, -2, etc., etc. Okay, so for right now, what we have is the expression that this is going to be that sum plus the entire function, and that's true on on the right half plane for now. Okay, so the claim is that this thing on the left is a meromorphic function with poles at the right places. Okay, and Stein proves this as follows. He says, well, let's consider the disk, fix some r, and then consider the disk of radius r. And then break the sum into two parts. We'll break it into a finite part up to some n, and then from an infinite part from n plus 1 onwards. Okay, and you choose n bigger than 2r. Okay. Okay. So then look at the second term. Consider the second term. Yeah. So. So for S in our disk, and for n bigger than n, bigger than capital N, which is bigger than 2r, we see that -1 over n factorial n plus s is of course smaller than 1 over n factorial times r, right? Right, because s is smaller than r, right? S is smaller than r, and n is bigger than 2r, right? So this n plus s is at worst, this is bigger than r for sure. Right. And so what does that give you? That gives you that the second part converges uniformly, right? So we get uniform convergence, right? So term 2, second term converges uniformly. And so is holomorphic on S less than R. So that second term is holomorphic on the disk. Okay. And then the first part, the first term is just a finite sum. Right? It's just a finite sum. It's definitely meromorphic. Meromorphic on the disk, and it has poles in the right places, right? With poles and correct residues in the right places. Okay, so what does that give you? That gives you that, right? That gives you that, that this thing in this disk, right? In this disk, the thing that we in this disk, this thing is a meromorphic function with poles in the right places, right? And this disk was arbitrary, right? So since R, right, R was arbitrary. Since R was arbitrary, we know that the sum is what we wanted, right? Is a meromorphic function on the entire plane with poles in the right places and the right residues. With the correct poles and residues. Okay, so right, so right. So again, we make kind of a similar argument to the how we showed that the functional equation was true. So let me sort of say where we are right now. Okay, so what we've shown is that the gamma function has this expression, right? Right. Initially, we start off with this expression. So initially, we start off with this expression, and it's valid. It's valid on the right half plane. Okay, right. And then we observe that actually this right hand expression makes sense on the entire plane, right? As a meromorphic function on C with poles in the right places. Okay. Now this thing, it's the same sort of argument. This thing agreed with the gamma function on the right half of the plane, and so it's going to agree with our extension. We had a previous extension. I'll call it like gamma in quotes. Right? We had a previous extension to the entire plane, making this a meromorphic function on the entire plane. Right? Now we have another one, right? And this one agreed with that one on the right half plane, and so it must agree everywhere. Right? And so that allows this formula to hold for the entire plane. Okay. Does that make sense? It's exactly the same sort of analytic continuation argument. Right. So the bootstrap version agrees with this one on the right half plane, both of them define meromorphic functions on the entire plane, and so they must agree on the entire plane. Okay. Okay, everybody all right? Okay, so so now we're going to switch. We want to get some expressions for the reciprocal of the gamma function. And kind of what I hope to get to by the end of this is we'll get the Hadamard factorization of the reciprocal. So I'm not sure if we'll make it, but we'll try and get there. Okay. So our goal basically right now is to get the Hadamard factorization for 1 over gamma. Okay, so the first thing we're going to do is get the following theorem that says that gamma of s times gamma of 1 minus s equals pi over sine of pi s. Okay, and this is at the end of class last time I mentioned that gamma of 1/2 is going to be the square root of pi, and this is where that comes from. Okay, so the proof of this turns out to be just a huge calculation. So get ready for some pretty dull calculation coming up. Okay, so we just write it out. This is going to be so we take the expression for gamma, throw in gamma 1 minus s. Right? We get this double integral. E to the negative t to the s minus 1, integral from 0 to infinity, e to the negative u minus s, du dt. Okay. If we do a change of variable, let u be vt. And of course du is going to be t dv. And so we get the integral from 0 to infinity of ts minus 1. We get t 0 to infinity e to the negative vt dt to the minus s dv dt. So we just do a change of variable. Some cancellation occurs. You end up with e to the negative t 1 plus v v to the negative s dv dt. And it's then you use Fabini's theorem to change the order of integration. Right. So we get we're going to integrate with respect to t first. right? You do the integration and you get the integral from 0 to infinity, v to the negative s over 1 plus v dv. Okay. Okay. So so there's a lemma that for alpha between 0 and 1, the integral of v to the alpha minus 1 over 1 plus v equals pi over sine pi alpha. Okay. So I'm just wondering if I should do this or not. So basically what happens is that you get that this thing equals this integral, x alpha as e of dx. Okay, so you do a change of variable, and then it gets to this. Okay, but this is actually an integral that we saw earlier. That we did earlier when we were doing contour integration. Okay, so this is something that was back in chapter 2. So this was one of the examples of the contour integration. So that's where that comes from. Okay, and so that gives you this that this equals pi over sine pi 1 minus s. Let's just say pi over sine pi s. Yeah.
Why do we know that 1 minus s is between 0 and 1?
Oh, yeah, I'm sorry. You prove it only for s between 0 and 1 initially.
Ah.
Yeah, sorry. I should have said. Prove for s between 0 and 1 initially, right? And then
and then our functional equation.
actually
gets us the
same
reciprocal.
sort of thing, right? Because it's interesting, right? Because you only prove it on this this segment here, but that's enough to get you on the whole plane by analytic continuation. Thank you. Okay. Okay, so I know this is not maybe not the most interesting thing. I'm regretting having put it up. Okay, but in any case, remark that this gives us some formula for 1 over gamma, right? 1 over gamma is going to be gamma 1 minus s sine pi s over pi. Right? So it gives you a nice formula for 1 over gamma, which is why we wanted it. Right. And then the second thing to notice is that this also implies that gamma is never 0. Okay. 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 So that was just a like a calculus exercise in some sense. But it allows us to get the following to get the following lemma. So this is the lemma that's going to help us get to get the Hadamard factorization. Okay, so the lemma says the following, that 1 over gamma is an entire function with simple zeros at s equals 0, -1, -2, etc., and only at, so at and only at those places. And then the second part is that 1 over gamma satisfies this sort of growth, Right, and thus 1 over gamma's growth is the rate of growth is less than or equal to 1. Right, because we have this s log s term, right? So we can make it slower than any s plus epsilon. So the growth is, so the rate of growth is less than or equal to 1. Yeah, Noah.
Should that be the magnitude of s to the 1 plus epsilon, not s plus epsilon? Since otherwise I feel
Oh
like
yeah,
it
I'm
would be
sorry.
complex.
Yeah, that should be, yeah, thank you. Thanks. Okay, so yeah, let me show you how okay, let me oops, sorry. Okay, so the first part is pretty straightforward, right? That this is going to be an entire function, right? Because we just use the equation that we just got. Right. So right, this part has simple poles. Has simple poles at 1, 2, 3, etc. Right. And then this guy, this thing has simple zeros at all the integers. Right. So those poles will cancel. The poles will be canceled out. And so we're going to end up with a function that has, zeros at 0, -1, etc. Right, so we get an entire function with simple zeros in the right places. Right. So So I have to say that I haven't finished working out the second part, so I'll try to do it next time. But so yeah, there was something where Stein said this part is clearly something something, and I couldn't figure it out. So I'll try to have that done next time. But in any case, let's just assume that for now. Okay, yes.
Haven't we proved this? The identity that we're using at the beginning of the proof. I thought we proved this for all of C, but take away something that looks like the negative integers. So how do we know that this is true on the negative integers? No, or is it defined, or is it true everywhere?
Is it just that you can make some argument about it's true in a close enough neighborhood around it, and because sign like has a 0 and this has a pole, it cancels and it's true at the point as well?
Or can we prove that gamma s times gamma 1 minus s is actually entire because there's zeros and poles?
The gamma has zeros. So it couldn't cancel itself. If gamma had zeros, then one of the gamma would be entire.
I guess this is just true by if the only points we're unsure of is where the left side here looks like loosely 1 over infinity, right? So the left side looks like 0. And then the other side has to be 0 because the sign term has zeros everywhere in the integers.
Mm-hmm.
Okay, sorry.
Okay, thank you. Yeah. Yeah, okay. Yeah. Okay, so sorry, so the factorization that we want to get is this one, that this thing actually equals e the gamma s s times 1 plus s over n e to the negative s, and from 1 to infinity. Yeah. Okay. Where okay, so sorry. Let's think for a second. So this thing, right? By that is entire, and of growth order less than or equal to 1, and has simple zeros. At 0, -1, -2, etc. Okay. So Hadamard says that that it's going to look like you know, something like this, right? E to a linear function. Right, it's going to look something like this, right? And okay, so okay, so actually, before we do that, let me see what I mean by gamma. So what's this gamma? This is something called the Euler constant, or the Euler-Mascheroni constant. And that's defined as the limit of the difference between you know, between this and the log. So I don't know if you've seen this before, but you know, basically, you know, you have, you know, the 1 over x function, right? Right. Right, and you take, you know, you take 1 over n, so you take, you know, 1, a half, a third, a fourth, blah, 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 up to 1 over n, and then you subtract off, you know, you subtract off log n. That's to say the area under this curve here. Right. So if you shift, you know, if I shift everything over to the right, it looks like you're taking right, up to n, and then so you take you know, you take the difference between these areas and the curve 1 over x, right? So you have the difference. So you take the sum of these areas, right? Plus this 1 over n at the end. So that's what this is, and as n goes to infinity, this converges to something. Do you want to see the convergence? It's kind of cute. I don't know. Okay. So why does this converge? If you take this and you express it as you express the log as an integral, right? And then we'll just write it as summation. You know, we'll basically write it as this difference here, right? So n goes from 1 to n to capital N minus 1. The integral from n to n plus 1 of 1 over n minus 1 over x dx. Right. So that each of those things gives you that little area there. Right. This. Right. Each of those gives you one of these areas, but then at the end we need to add on the 1 over n, right? Because there's that 1 over n at the end. Okay. Then if you can use the mean value theorem to see that, that 1 over n minus 1 over x is controlled by 1 over n squared on n plus 1. So that's just a straightforward application of the mean value theorem. So that tells you that that these terms, let's call them a sub n, right? That the size of the a sub n is smaller than 1 over n squared. Okay. So what we get is that this thing looks like some sum of terms plus 1 over capital N, right? But then as n goes to infinity, this thing converges, this thing goes to 0, right? And so this thing converges, and so this thing also is going to converge, right? And so it converges to this number gamma. Okay, so in any case, this number, this limit actually does converge, and it's going to show up. It's going to show up here in a second. Okay, so let's get that. So. Right now, we have that, we know that 1 over gamma looks like something like this. Okay. Okay. So we're going to divide both sides by s. Divide both sides by s, and then take the limit as s goes to 1. I'm sorry, as s goes to 0. Sorry. Okay. This, by the functional equation, is going to be 1 over gamma of s plus 1, right? So as s goes to 0, we get gamma of 1, which is just 1. Okay. So the left-hand side is 1, and 1 equals e to the b, and then this thing is going to turn into, again, 1, right? Yeah, no.
Why are we allowed to switch the order of the limit as s approaches 0 and then the limit that is inherent in the infinite product?
That is, there's a uniform convergence that occurs.
Okay.
Yeah, so that's actually okay. Okay. In any case, so b has to be 0, or it could be like 2 pi n I or something like that. But it doesn't matter. We'll just take it to be 0. That won't change anything. Okay, so then we have b is 0, and we plug in s equals 1. Yeah, plug in s equals 1 on both sides. Okay. So what we get then is that 1 equals e to the a times this thing, 1 plus 1 over n e to the negative 1 over n. It goes from 1 to infinity. Okay. That is to say that e to the negative a is the limit as n goes to infinity of, of this product. But that is the same thing as e to the sum from n equals 1 to capital N of log 1 over 1 plus n minus 1 over n. Okay. Yeah. So yeah. So now this part here. Sorry, let me. So we end up with the limit as n goes to infinity of summation, negative summation 1 over n from n equals 1 to capital N, and then we have this thing n equals 1 to n minus 1 log 1 plus 1 over n plus the last term, log 1 plus 1 over capital N. Oops, there should be an E there. Okay. Right. But this, if you work it out, this just turns into log of capital N, because you end up with this is, as you see, it's log 2 plus log 3/2 plus log n over n minus 1. Right. And so all those things cancel out, and you just left with log n. Okay. So what do you get? Right. The limit as n goes to infinity of e to the negative this sum from 1 to capital N plus log n plus this log 1 plus 1 over n. And then as n goes to infinity, sorry, there should be a plus here, you end up with e to the minus gamma. Okay. So you see that's where the gamma shows up. This is negative gamma. Right. This term goes to 0, right? And then this thing goes to negative gamma. Okay, so that tells you that A is gamma plus possibly some 2 pi plus possibly some 2 pi ik, right, for k in Z. Okay, so so that gives you that 1 over gamma equals e to the gamma plus 2 pi I k times times s times 1 plus s over n to the e to the negative negative s over n. Okay, but then you can get rid of this. You can. I'm sorry. There should be an s here. Sorry. That times s, and then times s, and then another s here. Sorry. Okay, but you can get rid of this 2 pi ik by noticing that gamma of s for right, but then you notice that since for s for s real that gamma of s is real. So for positive s, this gamma of s is real. So if so k must be 0, right? Because if k were non-zero, then you could end up with some complex values for by substituting an appropriate s. Okay. So that k has to be 0. Okay. So that gets rid of that. And gives you the factorization. Okay. Okay. So yeah. So that that's the proof of the factorization. But I have to say that we've kind of left the hard part aside, right? The hard part is to show we still have to get that last part, which is that that it has the growth, the growth of less than or equal to 1. Okay, that's it. Okay, that's where I'm going to stop today. Okay, so see you guys next time. Unless there are any questions. Any questions? Oh, I have your exams. Let me give you back your exams. Yes.
We get e to the minus gamma over there.
Yeah,
But
and
then we drop the negative sign.
the negative.
We're solving for e to the minus a.
So we're solving for what
Oh,
a
right.
was, and e to the negative a turned out to be e to the negative gamma. So
Oh,
a
yeah.
is gamma.
Right.